Hello everyone, welcome to the first video in this new series. In today's video, we will be exploring in depth the internal processes, characteristics, features, and life cycle of the Sun. So sit back, relax, and enjoy the video, because we're going for a ride, sunshine. So what is the Sun anyways? Derived from the Latin word sol, as in solar, the Sun is the heart of our solar system, being a hot ball of hydrogen and helium gas that formed about 4.6 billion years ago, and whose gravitational pull holds the entire solar system together. The Sun originates from a giant spinning cloud of gas and dust we call the solar nebula. As the nebula collapsed under its own gravity over time, it would spin faster and flatten out into a disk, with most of the material being pulled towards the center to form the Sun. Our star accounts for roughly 99.8% of the total mass in our solar system. The rest of the material form the planets, moons, asteroids, and other objects that now orbit the Sun. Currently, our star is orbited by 8 planets, at least 5 dwarf planets, tens of thousands of asteroids, and at least 3 trillion comets and ice bodies. The formation of our Sun in its main sequence phase enables the process of nuclear fusion to occur within its core. This is the process of plasmic hydrogen combining to form plasmic helium, which releases an abundance of energy. In fact, every second, the Sun fuses about 620 million metric tons of hydrogen into helium, which generates the equivalent energy of 100 billion tons of dynamite exploding every second. This release of energy creates an outwards pressure that counteracts the constant contraction every star faces from the force of its own gravitational fields. As for the future of our Sun, like all stars, our Sun will eventually run out of energy. When it starts to die, the Sun will expand into a red giant star, becoming so large that it will engulf Mercury, Venus, and possibly Earth as well. When the core of our now red giant star fuses to carbon, and fuel within the Sun runs out, our star will undergo intense solar activity and generate extreme solar winds that will eventually expel the Sun's outer layers and form a planetary nebula. The remaining dead carbon core would then be reclassified as a white dwarf star, which is not capable of creating nor emitting new energy. With no more energy to start nuclear fusion, the Sun will cool down over the course of billions upon billions of years, eventually cooling to the background temperature of the universe and becoming a black dwarf star. This aftermath of our star isn't what we are primarily concerned about in this video, however. So let's take a step back to our current yellow dwarf star. Located in a spiral arm called the Orion Spur that extends outward towards the Sagittarius arm in the Milky Way galaxy, this 4.6 billion-year-old yellow dwarf star and the rest of the solar system orbits clockwise throughout the galaxy with an average velocity of 450,000 miles per hour. Even with such speeds though, it still takes us about 230 million years to make one complete orbit around the Milky Way, as the Sun's orbit is roughly 25,000 light-years away from the galactic center. Furthermore, the Sun rotates as it orbits the center of our Milky Way galaxy, having an axial tilt of 7.25 degrees with respect to the plane of the planet's orbits. And since the Sun is not a solid body, different parts of the Sun rotate at different rates. For instance, at the equator, the Sun completes one full rotation every 25 Earth days, but at its poles, the Sun rotates once on its axis every 36 Earth days. Now for the composition of our star. The Sun is made up of super hot electrically charged matter called plasma. Our star generates electric currents with its incredible creation of energy, in turn creating a magnetic field that is carried out throughout the solar system by solar wind, a stream of electrically charged gas blowing outward from the sun in all directions. We'll get more into that later. About 3/4 of the sun is hydrogen, which is constantly fusing together and creating helium. Helium makes up almost the entire remaining quarter. However, about 1.69% of the sun's mass is made up of other gases and metals, such as iron, nickel, oxygen, silicon, sulfur, magnesium, carbon, neon, calcium, and chromium. Although this 1.69% may seem insignificant, this mass is still over 5,000 times the mass of the Earth. Along similar lines, the Sun is 333,000 times more massive than the Earth, with a radius of about 700,000 kilometers. But that's enough on the sheer magnitude of our star compared to us. And now on to the different layers of the Sun. To frame this next section of the video, we're going to start at the very center of the Sun and work our way outwards as we explore the inner workings and functions of this celestial object. The core is the hottest part of all stars, with the Sun's core reaching temperatures of 27 million degrees Fahrenheit, which is hot enough to sustain nuclear fusion. The core is about 86,000 miles thick, with an average density of about 150 grams per cubic centimeter. Since the core is the only place where nuclear fusion reactions occur, the rest of the Sun's layers are heated from nuclear energy created there. This fusion, however, creates two types of energy, photons and neutrinos. Photons are particles of light, which can consist of various forms of electromagnetic radiation. Neutrinos, on the other hand, are much more difficult to detect and only account for about 2% of the Sun's total energy. The Sun emits photons and neutrinos in all directions all the time, keeping up a constant flow of energy. Next layer beyond the core lies the radiative zone, which extends for the next 45% of the Sun's radius. In this broad zone, heat from the core cools dramatically from 7 million Kelvin to 2 million Kelvin. Energy from the core is carried outward by thermal radiation. During this process, radiation in the form of photons that were released in the core travel a short distance, are absorbed by a nearby ion, then released by that same ion, and then absorbed again by another. This occurs continuously throughout the radiative zone, delaying the evidential release of photons from this layer by about 170,000 years. Following the radiative zone is a transition region called the tachocline. This distinction of this region is due to the Sun's differential rotation. Material within the radiative zone versus the convection zone rotate at very different velocities, which cause the rotation rate of the Sun to change rapidly within the tachocline. Beyond the tachocline, naturally, lies the convection zone, where the temperature drops below 3.5 million degrees Fahrenheit. Here, large bubbles of hot plasma move upwards towards the photosphere via thermal convection through thermal columns, as the Sun at this layer is no longer hot enough to transfer energy via thermal radiation. When the hot plasma reaches the outer limits of the convection zone, it cools down and plunges back to the bottom of the convection zone, where it is subsequently heated up again, causing a cyclic motion of material in this layer. This marks the end of what is considered the interior of our Sun, as beyond this lies the surface and atmosphere of our star. As material rises up from the convection zone, it eventually reaches what we call to be the surface of the Sun, known as the photosphere. This layer is relatively cool, holding temperatures of roughly 10,000 degrees Fahrenheit, and is about 250 miles thick. Known to emit the most visible light, this layer is what we see from Earth with our eyes. However, it should hopefully go without saying that we should never look directly at the Sun without protective equipment for our eyes. The photosphere happens to be where most of the Sun's radiation escapes outwards into space. Notably, this layer happens to be where many of the star's distinctive features take form, such as sunspots, solar flares, and solar prominences, to name a few. We will be expanding upon these features shortly. However, before we explore there, let's continue with the few remaining layers of our Sun. Extending further outward is the chromosphere. Of a pinkish-red color, the chromosphere is about 2,000 kilometers thick and filled with jets of hot gas. At the bottom of the chromosphere, where it borders the photosphere, the Sun is at its coolest of temperatures, reaching 4,400 Kelvin, which gives this layer its pink color. The temperature in the chromosphere, strangely enough, increases though the farther you go out, reaching 25,000 Kelvin at the outer edge of this region. As previously mentioned, the chromosphere gives off jets of burning gases called spicules. These grass-like tendrils of plasma burst up from this layer at speeds as fast as 60 miles per second, capable of reaching outwards thousands of kilometers in height before collapsing and dissolving. However, spicules only last for about 15 minutes, limiting how far they are able to extend outwards from the chromosphere. Beyond the chromosphere lies an unofficial layer called the transition zone. Located in between the chromosphere and the corona, this thin layer is where the chromosphere rapidly heats up and becomes the corona. The distinction of this transition zone is due to everything below the transition zone being governed by gravity, gas pressure, and different processes of exchanging energy. Above the transition zone, though, the motion and shape of the layers are much more dynamic and tend to be governed by magnetic forces, which control solar activity such as coronal loops and solar wind. This leads us to the final layer of our Sun. Both Latin and Spanish for crown, the corona layer of the Sun peculiarly reaches temperatures of up to 3.5 million degrees Fahrenheit. This is still a mystery to scientists due to the counterintuitive nature of the corona layer being significantly hotter than the layers below it. This is the equivalent of walking away from a bonfire, for instance, only to get warmer as you walk farther from the heat source. Being the outermost layer of the solar atmosphere, this wispy layer can extend millions of kilometers into space and is home to countless solar phenomena and activities. Now for some key features of the Sun's atmospheric layers that were just detailed. Let us begin with sunspots. Appearing as dark holes within the photosphere layer of the Sun, sunspots are slightly cooler areas in this layer, which are created by bits of our star's magnetic field poking out from the interior into the Sun's atmosphere. Capable of lasting from days to months, sunspots range in size from 1,000 to 100,000 miles. However, the number of sunspots seen on our star varies as solar magnetic activity does. In what is known as a solar cycle, the Sun undergoes an 11-year process which ends with the rapid reversal of its magnetic poles, in other words meaning the North and South Pole swap. But there will be more on the magnetosphere in a bit. Also occurring in the Sun's photosphere layer, solar flares are tremendously energetic bursts of particles and light triggered by the release of magnetic energy on the Sun. By far the most powerful explosions in the solar system, solar flares are dependent on the creation of sunspots in order to form, as sunspots create a magnetic connection between the photosphere and the corona layers of the Sun. Along similar lines, the formation of solar prominences also depends on sunspots. This is because solar prominences, also known as filaments, are coronal loops of cooler, denser solar material that erupts when the magnetic structure becomes unstable. Following this violent road, coronal mass ejections, or CMEs, are also capable of being triggered by disturbances within the Sun's magnetic field, often forming near active regions of sunspots after a solar flare. CMEs are immense clouds of magnetized particles blasted into space by the Sun at over 1 million miles per hour. Capable of producing great geometric disturbance, coronal mass ejections have been known to ignite bright auroras, short-circuit satellites, and even destroy power grids here on Earth. Near the Sun's poles, something called coronal holes can form. A coronal hole is a colder, darker patch of the Sun's atmosphere, with much lower density than the surrounding areas. These areas on our star can form due to connections of the Sun's magnetic lines into interplanetary space. allowing some of the fastest moving particles of the solar wind to pass through. As for what solar wind is though, these are groups of extremely hot, charged particles that reach an escape velocity of 400 kilometers per second, allowing for them to escape the sun's gravitational pull and disperse throughout the rest of the solar system. Blowing in all directions, solar wind is capable of spanning over 10 billion kilometers away from the sun, defining the area in space to which the sun has an influence over, called the heliosphere. Directly connected to this heliosphere, however, is a magnetosphere, which, in case you couldn't have guessed, pertains to the sun's magnetic field that pervades our entire solar system. Carried throughout the solar system by solar wind, the magnetosphere greatly influences solar activity and events, which are confined to a repeating pattern called the solar cycle. Briefly mentioned earlier in this video, the solar cycle is the process of the sun's magnetic north and south poles swapping every 11 years. Consequently, from this swap, the sun's photosphere, chromosphere, and corona layers change from quiet and calm to violently active. During the height of the sun's activity cycle, known as a solar maximum, is a time of greatly increased solar storm activity. Sunspots, eruptions called solar flares, and coronal mass ejections are common at solar maximum. Solar maximums are known to host several flares per day, whereas during solar minimums, there may be fewer than one per week. Solar activity doesn't just concern the sun though, as due to solar activity releasing huge amounts of particles and energy throughout our solar system, this creates a phenomenon called space weather, which can influence other planets such as our own. Space weather can interfere with satellites, GPS, radio communications, as well as cripple power grids and corrode pipelines that carry oil and gas. The strongest geomagnetic storm on record is the Carrington event, named after the British astronomer Richard Carrington, who observed the event on September 1st, 1859. Triggered by a massive solar flare, this solar activity sparked discharges that electrocuted telegraph operators and set telegraph paper on fire. The Carrington event also created auroras which were visible as far south as Cuba, the Bahamas, Jamaica, El Salvador, and Hawaii, lighting up the night sky as if it were day. With such dangerous and disruptive events on our world, it is no wonder that if such an event were to occur today with increased technology usage, it would have extremely devastating consequences on our modern world. But until that day, let's be grateful for the technological tools and devices we have often taken for granted these days. As with the spark of a single solar event, these electrical devices could all be fried beyond repair in an instant. With power grids exploding, planes crashing, and phones frying everywhere, people would be forced to return to a screenless world that used to be the norm not so long ago. And that doesn't sound too bad, does it? Thank you all for watching. If you enjoyed this video, please consider liking and hitting that subscribe button with the notification bell on. To learn more about the sun, see the links to the research I used for this video in the description. If there are other ideas you'd like to see covered in a future video, please leave it in the comments below. Have a great day everyone, and remember to stay curious.